Welcome to a tutorial on the 8085 microprocessor, and well, we're gonna revisit the 8255 chip over here once again, and we're gonna discuss about the control register. Now, from the previous tutorial, okay, we got to know that the control register, okay, is basically an 8-bit register, okay, present in the 8255A chip, okay. And it is this control register, or the presence of this kind of a register memory in the 8255A chip, that basically makes it programmable, okay. So we can assign some instructions, okay, and basically those instructions form a pattern of binary codes that is stored in the control register that just helps the 8255A function in the way we want it to. Okay, so using the programmable feature of this chip, we can use either of port A, B, or C as the input and output ports. Okay, and we can also enable different kinds of functions in these ports. So here we're going to visit this particular thing in detail. Okay, next, what we need to learn now is how to program the control register. Okay, now you should always keep in mind that each of the bit positions, okay, in the control register, okay, has a significance, a different significance, and the 8-bit binary code that we're gonna put over here in the control register, of course, we known as the control word, okay, or rather the 8-bit control word. All right, so we're gonna write or store the 8-bit control word into the control register to control this 8255A chip in the very way we want it to. Okay, so let's just start with D7 over here. So the D7 bit, okay, that is this particular position. Now this position, each of the registers, so we can see that it's basically an 8-bit register, so each of the register cells can hold either a 0 or a 1. Right? So if in D7 we put 0, okay, a logic 0 voltage level, or rather, yeah, that's better, then this would basically indicate a condition, okay. If we just put 0, then the entire chip would be just sent to the BSR mode, okay, or rather the bit set reset mode. Okay, I'm gonna write that down over here. Yeah, there you go. Now the bit set reset mode is a little bit off your level right now, so we are going to discuss the BSR mode detailed, okay, in detail in a later tutorial. Okay, but other than the BSR mode, okay, we can also operate the chip in the simple input output mode. So in order to do that, we are supposed to assign a logic 1 over here in D7. Okay, so in that case, if there's a logic 1 in bit D7 position, then the chip operates in simple input output mode. Okay, so this is simple input output mode. Now while in the simple input output mode, okay, we can select any of the ports A, B, or C, and assign them as input ports or output ports and just control the devices connected to them. Okay, right, so after we just learned about these, now we need to keep in mind that this chip is a little bit complex in operation, in the fact that it has a lot of modes and sub modes that it basically operates in. So in the simple input output mode, okay, whenever the D7 bit is assigned to logic 1, then this mode can be defined, or rather divided, further subdivided into 3 major parts. Okay, so that is mode 1, okay, then we have mode 2, and finally mode 3. Okay, or rather I might write it in this way, then it'll be easier for you all to get. This is referred to as mode 0, mode 1, and mode 2. Okay, so when we're operating when we are basically operating the chip in the input-output mode, then it has basically three ways in which we can just operate the input-output function of this particular chip: the mode 0, mode 1, and mode 2. So while in mode 0, all the three A, B, and C ports are basically simple input-output ports. So they are basically simple I/O ports. Okay, but while in mode 1, the ports A, B, and C are, they basically behave as handshake input-output ports. Okay, so they just exchange handshaking signals at this particular mode. Okay, and now in mode 2, what happens is that the port A becomes a bi-directional data bus. Okay, so it just becomes a bi-directional data bus, while port B can be set in either mode 0 or mode 1. Okay, so if we're just selecting mode 2 for the entire chip, then we can set A as a bidirectional port, B either in mode 0 or mode 1. That is basically optional, and we can use, or rather set the port C, or rather port C is basically usable as a handshake input-output port. Okay, so there you go. So this is basically what happens whenever we select the 8255A chip in the input-output mode. Okay, that is if we just assign the bit D7 as logic 1. Okay, now generally if we are dealing with simple input-output procedures over here, okay, so we'll just basically do that, because in order to just keep things simple right now, since we're just beginning to learn about it, so in order to just keep things simple right now, we are gonna basically work with mode 0, okay, and assign the A, B, C ports as simple input-output ports. Okay, and we shall discuss or elaborate about the mode 1 and mode 2 cases later on. Okay, now since we selected the mode 1, that is input-output port, so we're gonna basically write down logic 1 in place of D7. Okay, right, so next comes the further important two more bit positions. Okay, that is D6 and D5. Well, while we're working with the bits D6 and D5, then comes, which is only necessary whenever we're operating the 8255A chip in the input-output mode. Okay, that is if we have just assigned a logic 1 voltage level at the bit D7, then we're supposed to worry about D6 and D5. Okay, under the BSR mode, if we would have put a logic 0 in place of D7, then in that case we wouldn't have worried at all. Okay, with the bits D6 and D5. Okay, so under the simple input-output mode, okay, that is whenever the bit D7 is set to logic 1, okay, we need to now specify in which mode would the chip operate, whether it be mode 0, mode 1, or mode 2. Okay, so now if we are supposed to work with, I'm just gonna write that down over here. If we're supposed to work with mode 0, then we would put, okay, I'm just writing here D6 and D5. So we're supposed to assign both D6 and D5 at logic 0 voltages. Okay, and on working with mode 1, we need to put it as 0, 1, okay, in this particular order. And for mode 2, okay, if D6 bit is set to 1, okay, then only the chip basically moves on to the mode 2. Okay, and the D5th bit is a don't care condition, meaning it could either be 1, 0 or 1, 1. Any of them would do. Okay, so it's not a problem. So now since we're more interested to work with the mode 0 right now, so we're supposed to put both D6 and D5 bits at logic 0 voltage levels. Okay, so here goes. Alright, so the explanation for the D6th and the D5th bits, well, they basically are given over here. So I would like to draw your attention to this particular table. Okay, so this is a table over here which defines it all. Right, now okay, now before we move on further, we need to clear the area a bit. Alright, so now that seems a little bit clearer. Okay, now we come to the D4th bit over here. Now the D4th bit will control the status of port A. Okay, so here this particular bit will control the status. Okay, I'm just gonna take it a little bit lower. Okay, right over here. Okay, so this controls the port A. Okay, now if we're supposed to designate the port A as an input port, then we're supposed to store a logic 1 over here. So then we can basically use the port A as an input port, and if we would store the logic 0, then port A becomes an output port. Okay, so each of the ports A, B, and C, they have 8 lines. Okay, so each of the ports are 8-bit ports, parallel ports. So for port A, this is what happens: 1 for input, and if we write 0 over here, then it becomes an output port. Okay, so there you go. Now we haven't decided yet whether to assign port A as input or output. Well, we don't know yet, but that'll we'll basically come to later on. So after that we have a port 3, port D3 over here, or rather the bit D3 in the control register. Okay, so now the the register cell, that is D3, or the register bit D3. Now this D3 bit is used to control the port C upper. Okay, so this is used to control port C upper. Okay, so that's the upper C ports, ranging from C4 to C7. Okay, so the upper 7 ports, the 4 ports it is. So now here, if we would, again, it goes the same way as that for port A. If we'd write 1, then we shall use them, the 4 lines over here, as input. Okay, and logic 0 here would designate them as an output port. Okay, so that goes for port C upper. Okay, and next we have bit D2. Now bit D2 is used for mode selection. Okay, so this is basically used for mode selection for port B. Okay, now we can basically set port B both in mode 0 as well as mode 1. So in order to enable this particular feature, we have this particular bit over here, that is bit D2. Now if we'd basically write that down over here, so this is for mode selection, okay, of port B, right? So here if we'd basically put 0, then it is mode 0, or rather the port B is set to mode 0, and a logic 1 would basically set port B to mode 1. Okay, so that's the way you set this particular bit. Okay, next comes D1. We're almost done over here. Now for D1, let me just tell you, this is actually the control port, the control bit that will controls the port B. Okay, so now this is for port B. Okay, so now for port B, let me just tell you that if we put logic 1 here, then B becomes an input port. Okay, and a logic 0, B becomes an output port. It's pretty much similar to that in case of port A. So that's gone for port B. Okay, port B is done. And finally the last bit, that is D0. Okay, now this is used to designate the port C lower. Okay, port C lower, that is the bits ranging from, okay, let's just clear the area a little bit more. So we're gonna clear the area a little bit more. Alright, fine, that's it. So now we can basically write it over here. So port C lower ranges from that of C0 to that of C3. Okay, that's the lower 4 bits. Okay, now for port C lower, again we can basically set it to input and output, whatever we need. So 1 for input, okay, and 0 for output. So there you go. So all the 8 bits of the control register and their individual functions and significance has been discussed over here. Now we need to give you an example over here. Now let's just think about it. Now we saw that well, for port A at least there is no such mode, okay, but for port B we can see that, well, there is a mode 0 and a mode 1, okay. Now, well, B needs to operate as a simple input output port, so does A and C as well. So we need to put if we operate B in mode 0, okay, then in that case, right, so in that case B would just behave as a simple input output port. So we need to put a logic 0 in the bit D2 over here, right? And now let's just think of a problem statement. Okay, so now we have a problem statement over here. Well, the problem statement says, well, we're supposed to read inputs at ports B and C lower, okay. So we're supposed to read the codes from port B and C lower, okay. So they would be designated as input ports. So let me just categorize over here. So port B, okay, and C lower, they're going to be designated as inputs, okay, and output the same in port A and C upper. So on the other hand, if we're supposed to output the same code that we're reading from port B and C lower, then, well, in that case port A and C upper, well, they are supposed to be designated as output ports, okay. So we're supposed to read the data from port B and display that, or rather output that, at port A, and from C lower we're supposed to read another 4-bit data and output that through C upper, okay. So that's what we are supposed to do. So read from B, output at A, and then read from C lower and output at C upper. So this is the entire operation that's going to take place. Now before we move on to writing a program, okay, well, this process is entirely controlled by the program written in the the program that has been, well, assigned to the microprocessor to perform. Now this is, well, controlled by the program basically. Now in order to well, perform this operation, we need to think of the control word, the 8-bit control word. See, our control word is not complete yet. So we need to assign port B and C lower as input. So let's check out. So port B as input, so we need to put D1 at logic 1, okay. And, well, let's just check it once again. C lower is input also, so bit D0 needs to be set to logic 1 again. And, well, port A and C upper needs to be selected as outputs. So let's just look it up. So for port A, that is the bit D4 needs to be set at logic 0, okay, and C upper also at logic 0. So bit D3 at logic 0. So now this entire thing that we have over here is our control word for the purpose. So this entire thing is our control word, or 8-bit control word for this particular problem statement that we've just thought about. Now, we human beings will do well to remember binary codes in hexadecimal. So for this particular 8-bit number, that is 1,000 and then, well, 0011. So this is equivalent to 83H. So this particular thing, well, becomes the hexadecimal equivalent of the 8-bit control word. So this is the hex code, okay. So this is basically the hex code or hexadecimal equivalence. I'm also going to write that down over here. So hex equivalent, okay, of the 8-bit control word which we are supposed to send into the control register, okay. And once we've just loaded this particular data into the control register, then automatically port A and C upper would be designated as output ports, whereas port B and port C lower would be set as input ports correspondingly. And also the entire 8255A chip would be just sent to the input output mode, and then putting both zeros at D6 and D5 would basically set it to the simple input output. Would basically set it to the condition where port A, B, and C all will be set as simple input output ports, okay. So this is how you can use the 8255A chip, just an example over here. And well, in the following tutorial we're going to discuss about how to write a program to execute this particular problem statements. Okay, so till then it's just going to be a short goodbye for now, and catch us on our next tutorial.